Infrastructure is supposed to be reliable. You turn on the tap and water flows. You switch on the light and electricity is there. Most of the time, these systems just work. That reliability is not accidental. It comes from layers of control, redundancy, and human oversight. Now, those systems are becoming more efficient. AI models optimize energy distribution. They predict demand, adjust supply, and reduce waste. In water systems, AI can detect anomalies, forecast consumption, and optimize treatment processes. In logistics, it coordinates routes, inventories, and delivery timing. At first, this looks like clear progress: less waste, lower costs, faster response. And in many cases, it is. AI can process more data than human operators. It can identify patterns earlier, it can react faster. But something changes when these systems become dependent on that capability. Because efficiency and resilience are not the same thing. Consider a power grid. An AI system manages distribution based on real-time data. It balances supply and demand continuously. The system becomes highly optimized. There is less slack, fewer buffers. Everything runs closer to its limits. This improves performance under normal conditions, but it can reduce flexibility under unexpected ones. If conditions change in ways the system does not anticipate, there may be less room to adapt. This is not a failure of the technology. It is a property of optimization. Optimized systems are often less tolerant of deviation. A similar pattern appears in other areas. Water treatment systems may rely on predictive models to adjust chemical dosing and flow rates. Logistics networks may depend on AI to minimize delays in inventory. Each system becomes more precise, but also more tightly coupled. When components are tightly connected, disturbances can spread more quickly. A small disruption in one part of the system can affect others. There is a reasonable counterargument. Some argue that AI actually improves resilience. Better predictions allow earlier responses. Anomalies can be detected before they escalate. Systems can be monitored continuously. And this is true. In many cases, AI enhances reliability. It can identify risks that humans might miss. It can respond faster to changing conditions. But this introduces a different kind of dependency. If systems rely on AI to maintain stability, the absence or failure of that capability becomes more significant. In traditional systems, human operators play a central role. They understand the system. They intervene when something goes wrong. They adapt based on experience. As automation increases, that role can shift. Operators may oversee systems rather than control them directly. Interventions become less frequent. Familiarity with manual processes may decrease. This can create a gap. When automated systems function well, human involvement decreases. But when something unexpected happens, human understanding becomes critical again. If that understanding has diminished, response may be slower or less effective. There is also a question of visibility. AI systems often operate as complex models. Their decisions are based on patterns in data, not always on explicit rules. This can make behavior harder to interpret. If a system produces an unexpected outcome, understanding why can take time. And in infrastructure, time matters. Second-order effects can emerge. As more systems adopt similar technologies, dependencies may align. Multiple infrastructure networks may rely on similar models, data sources, or software platforms. This can increase systemic risk. A shared vulnerability can affect multiple systems at once, even if each system is individually well-designed. Another factor is external influence. As infrastructure becomes more connected and data-driven, it also becomes more exposed. Cybersecurity becomes more complex. Data integrity becomes more important. If the inputs to an AI system are compromised, the outputs may be affected. And those outputs can influence real-world systems. None of this suggests that AI should not be used in infrastructure. The benefits are significant. Efficiency improves, costs decrease, performance becomes more consistent. But the trade-offs need to be understood. Optimization can reduce slack. Automation can shift human roles. Dependency can change how systems behave under stress. The challenge is not just technical, it is systemic. How do you design systems that are both efficient and resilient? How do you maintain human understanding in highly automated environments? These questions do not have simple answers. They require balancing competing goals. As AI becomes more embedded in infrastructure, this balance will become more important because these systems are not optional. They support everyday life. And when they work, they are invisible. When they do not, the impact is immediate. AI can make infrastructure more capable, but it also changes how that capability is structured. The goal is not just to make systems better, it is to understand how they change. Because the most important risks are often not the ones that appear suddenly, but the ones that develop quietly as systems become more efficient and more dependent at the same time.